Alrighty, let's see. Full screen. Here we go. Okay, so this is chapter 3. We're doing 3 sections in chapter 3 only. We'll talk more about that in class. This is section 3.1. This is called Solve Linear Systems by Graphing. And we're really going to push the graphing calculator in this section. The textbook has written its write-up without including the graphing calculator, but we will do that tomorrow in class, and I will show you how to use it. Okay, let's go through the vocabulary. System of 2 linear equations. So basically 2 lines. You're solving for the point of intersection. The book here presents both lines in standard form, which should look familiar, right? Especially the first equation, ax plus by equal to c. If you were graphing, you would typically always solve for y, or you could always graph using intercepts, and we'll talk more about that. The solution of a system is an ordered pair that satisfies each equation. So again, if you're given 2 lines and you're asked to find the solution, a possible answer might be 2, 3, for example. That's called an ordered pair, x, y. X is 2, y is 3. The system is called consistent if there is at least one solution, and I'd really underline, at least. So there could be more than one solution. That's kind of unusual, but typically we always have one solution, like 2, 3, for example. A system is called inconsistent if the system has no solution. So there is no solution. If 2 lines are given and they do not intersect, which would be parallel lines, then there would be no solution, and the system is called inconsistent. And then on top of that, we call a system independent, a consistent system that has exactly one solution. So systems are consistent and independent if there's one solution, and systems are called consistent and dependent if it has infinitely many solutions. Infinitely means just unlimited. There are 2, and this typically is when 2 lines are given and they are the same line. So it's sort of disguised in the equations, and we have an example coming up for that. All right, so here we go. Here's our first example. This is solving a system graphically. So you're given 2 equations, right? And you hopefully can recognize that they're both lines. Equation 1 I probably would solve using the intercepts. It looks like when x is 0, y is 2. And it looks like when y is 0, x is 1. So graphing this guy, I'd put a dot here and here, connect with a line. Ruler would be nice here. Second equation, I might not do the intercept form because the 3 kind of throws me off. I would probably solve this for y, and I think you should get 2/3 x, right, and -10/3 y. And so here, kind of not as fun. Should go down 3, which would be 9/3 and just slightly more. My slope is positive 2/3, so I'm going to go up, 1, 2, and over 1, 2, 3 here. And then I would, and again, this is tricky with my bamboo pen, but I'd go like that. And so the solution, it appears that the graphs intersect here. Again, a ruler really would be the perfect thing to do. I'm going to guess that the point of intersection is right around here. It looks like my line, this guy, I could have been a little bit straighter. Does that make sense? Again, I apologize. I'm not sure how to make a ruler, but I'm going to guess that my solution here is going to be 2, -2. And you should be sitting back going, gosh, this seems kind of strange. I would solve a system like this either by elimination or subtraction method, and that's absolutely correct, and we'll do that in the next section. Here I just would like you to appreciate that this system means that 2 lines, where they intersect, that's the solution. We're guesstimating, if you will, a ruler would have helped, that the intersection here is at 2, -2. Hey, and we can check this. This is kind of nice. Take the first equation, substitute 2 in for x, substitute -2 in for y, and hopefully you can see that 8 minus 4 is indeed 4, and that is check. Hey, that is true. And then if I plug this same point 2, negative 2 into the second equation, I can see that it's 4, right, plus 6, which is 10, and it is true. So that is the point of intersection. This point 2, negative 2 satisfies both equations. Again, hopefully you can see this the graphic sense of a system of equations. If you would, go ahead and maybe give this one a go. So you're given 2 lines. Go ahead and graph both lines and guess the solution, and then go ahead and check your guess back into the equations. And again, if you use a ruler and you're careful with your lines, you should have a pretty good estimate. Go ahead and hit pause, and when you're ready, hit play again. And there is the answer. So graphing both lines, get my pen here. Here is your estimated solution. Hopefully you are within that ballpark range. The answer is 1, negative 6, and just plugging both, negative 1 and, positive 1 and negative 6 into both equations, you should see that you had the right answer. I hope you got that one. So here's a great picture. This one is super important. So here are your 3 possible scenarios when you have a system of linear equations. This is always true. And you probably have dealt mostly with exactly one solution, right? That's typically what happens when you're given a system of equations. So you graph, you have 2 lines, and this is the one solution. The lines intersect at one point, and we call this system consistent and independent. Ooh. Still learning how to write with this pen. There we go. So the next possible thing is that you're given 2 lines, but they're actually the same line, so they can be scaled up, and we'll see an example of that. We call that infinitely many solution. Why? Because there are infinite, right? How many points would you like me to draw before? I could do this forever. It would be fun, right? There are just points, and I'm skipping. There's a million points in between every point. So again, we say that this the lines coincide, or they are the same line, and it is consistent and dependent. And I would urge you to write these words. Maybe even this, this chart would be on your note sheet for this section, and you can again have a note sheet for chapter 3. So finally, you could have what's no solution. So you do a system of equations and it doesn't solve. What happens there is when the 2 lines given are parallel, they will never intersect. So the lines here we say are parallel. And the system is called inconsistent. Here we go. Again, great chart to memorize or get on your note sheet, but really visually quite nice to see the 3 possible scenarios. So here's an example that will solve a system with many solutions. So again, many solutions means you're really dealing with the same line. So look at how the 2 equations are presented, right? At first glance, you'd say, hey, those are 2 different lines. But if you look carefully, you can see that every component of the first equation is actually multiplied by negative 2, right? You can see that would get you 4, right? 1 times negative 2 is negative 2, 4 times negative 2 is negative 8. So in this case, we're really dealing with the same line. And maybe you're not looking for that when you solve a system and you wouldn't see it, but as soon as you graph, you'd realize you're dealing with the same equation. I'd use x-intercept and y-intercept to solve here. So when x is 0 for equation 1, y is equal to 4. And then when y is 0, x is equal to negative 2. And notice if you went through the same scenarios for equation 2, set x equal to 0, y would solve for 4, same location. And when y is 0, x would solve for negative 2. So we're really just dealing with this one line that was, I use the word scaled up, right? Just multiplied by 2. So we are dealing, the graphs of the equations are the same. Same line. So each point on the line is a solution, and the system has called infinite length. Can you mind if I draw the infinite symbol? Infinite many solutions. Therefore, the system is called consistent and dependent. Again, consistent because there's an answer, dependent because there are many, many answers. Again, your choices here are consistent and independent. That would mean there's one solution, right? Consistent and dependent, infinite many solutions, or the same line. And your last choice is inconsistent if you have parallel lines and no solution. So maybe we should check the parallel line system. So here you can see the two equations. They look awfully similar, but notice they have a different, C value. And when we go ahead and graph these two lines, you would see the first one is at, I'd use x-intercept, y-intercept. I'm going to speed this up just a little bit. We know how to do this. I get this line here for equation 1. And then for equation 2, I should be at 0, -1, intercept, and 2, 0. And I get this line. And when two lines are parallel, then there's no solution, and we say that these are parallel lines. We use the parallel symbol. Hope that's all right. Therefore, the system is, we call, inconsistent, and more importantly, there is no solution. So here are 4 examples. Go ahead and give them a try, right? You should get the hang of it. Maybe before you even graph any of them, see which ones you can you find the ones that are the same line, so ones that are just scaled. Look at the two equations, see if you can see the scaling, and then maybe find the equations that are parallel. You should have two problems, that'll give you one solution, one problem that will give you infinite solutions, and one of the 4 that will give you no solution. Go ahead and hit pause, and when you're ready, hit play, and you'll see the answers. And there are the answers. Let me just check on my timer how we're doing. I need to wrap this up. So hopefully you were able to notice that for problem 3 that you multiplied everything by 2, and hopefully you noticed here with problem 4 that the equations look awfully similar except for this part, which makes them parallel. A last example to give you is going to be our word problem. The word problem. Here we go. So this is an ice cream shop. One customer pays $9 for 2 sundaes and 2 milkshakes. And the second customer pays $13 for 2 sundaes and 4 milkshakes. So here we write the total cost. We say that the X is going to be the cost of a sundae. We get 2 of those. So if a sundae cost $1, you'd spend $2. And the cost of shakes, you got 2 milkshakes. So there's your first linear system. The second one would be 13, and you would put 2 sundaes and 4 milkshakes. So again, writing these equations is, well, it's rather tricky. But the more problems you do, the better you get at that. I'm going to stop here because I'm running out of time. This again, you would solve this by graphing, or what we'll learn tomorrow or review tomorrow is solving using elimination or substitution method. Let's do some more word problems tomorrow in class. Okay, see you tomorrow.